right, well, let's start the afternoon session. So once again, joining us from CERN, we're happy to have Sasha telling us some more about scattering processes. Sasha, take it away.
Thanks, Oliver, and hi everyone. Thanks also Luca for swapping the order with me. Today will be the last lecture, and let me just, before introducing what the topic of what we'll be discussing today, remind you that last time we discussed this bounds on various observables, in particular bounds on the cross-section, and we discussed the derivation of this Froissart bound, which told that the cross-section cannot grow faster than a logarithm. And then I also told you that there is this perhaps data-driven models where you think of this emergent degrees of freedom, some kind of Regge field theory, which tries to attempt it. So let me actually connect this discussion to the data because it's interesting. And I just want to show you, so this is the data for the scattering, so proton-proton scattering. You look at the total cross-section, you look at the elastic cross-section, and you look at the inelastic cross-section as a function of energy. What do you see? Well, first of all, you see that they're growing. This is the first feature. Second, you see that they're growing slowly. You see that the inelastic cross-section is bigger than the elastic. And the fit that, say, the common fit which experimentalists use is this fit, which includes, in particular, this log square. Now, to connect to the previous lecture, let me tell you that if you apply Froissart bound and you calculate this number here using the Froissart bound, you will get 60. So you see that the data is far from saturating the Froissart graph. This coefficient is very small. And you can wonder, how do you explain that? One possibility, and this also connects to what we discussed last time, is actually that we should not be using this fit with the log square, which is some kind of asymptotic behavior of the amplitude, but we can just take a small power. And in fact, if you plug a small power, this is what I was called this Pomeron, which corresponds to this diagram, kind of. It fits also really well. However, you see that if you go to higher energies, this power always grows eventually faster than log square. Therefore, something must happen. Something must happen because otherwise you'll violate unitarity. It grows too fast. Now, what happens and how it happens is an interesting question. Which fit is good, this one or that one? How do you explain this number? How do you compute this? And these are questions which, of course, have been discussed in the literature widely, but to some extent, okay, well, if I give you the QCD Lagrangian, we do not know how to calculate these things. So it's an excellent problem, and this is exactly the type of problem which we cannot calculate on the lattice. And so it's a problem for say, theorists to figure out. Now, another fact. So this is just for, I guess, the few basic things I wanted to tell. Another interesting fact, you can ask, okay, so do we see this or do we see that? It's of course hard to tell the log square from such a small power. There is something interesting that happens is that if you look at what is known as differential cross-section, so differential cross-section here is just a square of this amplitude that we've been discussing all the time. And here, what you see, it's again a function of energy. This quantity B is something what's called diffractive slope. And basically, the way you should think about it, it's designed in such a way that imagine that your amplitude grows like a power, S, J of t. Then you take a logarithm of this function. And then you take derivative in t, and then you set to 0. So if it grows like a power, you will get j prime of 0 times log s. Therefore, if you have this power growth, then if you plot this b as a function of energy in the logarithmic scale, it should be a straight line. And here you see that this is the straight fit is working really well. And so this is something which is totally consistent with having something like this, just the power. However, you see that the last few points are off. And now, okay, what does it mean exactly? Does it mean that this model is breaking down, that we are transitioning to the Froissart growth? We have to include the multi-Pomeron exchanges, etc. Okay, I'm not sure it is understood fully, but you see, I just wanted to point out that even in this very, very basic observables, we're not doing something fancy. We're just looking at the total cross-section, differential cross-section. There is something very interesting happening, and very interesting also from the theory point of view, because this is not something we can calculate using Feynman diagrams or something simple. So it's really conceptual. It's a conceptual interesting problem in this very simple observables. Now, this was my comment about the previous lecture, and overall, when I introduced this problem, and okay, there are of course many ways to think about scattering, but I chose this angle of thinking of that as you start considering scattering, you face this multi-particle physics, and you have to do something about it. And I told you that there will be 4 solutions, and so first solution was we set, say, MP to be fixed and small, but it was not controlled. Then we say that there was MP agnostic, where we just say, okay, well, we have no idea. We completely give up. We just extremize observables. We don't need to know anything about it. We just press the button and see where we get. Then I told you that there is a more ambitious approach, perhaps, where you can try to build a MP model based on data, perhaps. This is what I briefly mentioned as this Reggie field theory. And today, this is the last solution, and it is Friday, so let's just enjoy a little bit, take a simple problem. Because what we discussed so far is very hard. These are very hard problems. So let's just do something simpler and some fun. And also, I want to consider a model where we actually know that the model exists. We kind of know how to solve it, more or less. How do you make things simple? Well, the canonical example is, say, if you take weakly coupled string theory, basically you take weak coupling, scattering, but it's still a non-trivial scattering where your amplitudes are meromorphic, and you have particles which scatter, and they exchange resonances, which are just another stable particles. You can label the external guys, L, you sum over the internal guys, and say this should be equal iterations like that. And this is say crossing equation. So you think of this as a particle exchange. Your amplitude, say t of st, is a meromorphic function. And here you see how why is multi-particle thing is simple, because, well, you can build amplitudes by gluing. So the basic element is these 3-point couplings, and just by gluing particles, you can build higher point amplitudes, 5-point, 6-point amplitudes, and so by making external particles whatever you want, in principle, you get this complete set of equations. And this is exactly also what happens in the CFT Bootstrap. You will have courses about this. This is the magic of CFT. You just have a set of complete equations where the basic elements are 3-point vertices, and then you glue as many particles as you want. So this is much simpler, because in a sense, this reduces the problem. Everything is just 2 to 2. There could be many different 2 to 2 amplitudes, but or in the case of CFT, 2 4-point correlators, but otherwise you can just go ahead. Now, it happens at weakly coupled string theory. Another famous example is a large N gauge theory. And you've probably seen, and in this case, the beauty of this problem, and you already know that it's simple. I was not able so far to write any explicit formula for the solution for the amplitude, say, in 4 dimensions. But here you can do that. And the simplest solution here for this object, which satisfies the basic properties, is the, say, Veneziano amplitude, which, for example, describes scattering of open strings. Here it is an amplitude which is meromorphic. You see it has poles. These poles are simply these resonances that you exchange, and their masses, the poles are at integers, when s or t equal integer, and this amplitude is crossing symmetric. It satisfies all the basic properties. It's unitary, blah, blah, blah. Now, this model is very old, and can we do a little bit better? Not a little bit better, but this is a very simple amplitude, and perhaps we can try to make something, to deform it in some way, or make it a little bit more complicated. And people have been discussing in the last few years various deformations of this function. And okay, you can cook up many deformations, but most of the time you do not know if there is a theory behind. So, and instead I want to focus on the theory to make sure that we know what we are doing actually corresponds to something. And we are not simply writing some functions. Now, what is the model that I would like to consider? The model is very simple, is that imagine you have, let's start the following. Let's say we will be considering scattering of some particles, and we want to consider, say, some kind of quark and anti-quark. And if we want to do, say, QCD, well, the interaction is complicated, or perhaps is you have some Coulomb potential. So if there is a distance L between the charges, so this is just the distance, then you could have some perhaps confining potential or some whatever complicated things. And as I said, I want to make things simpler. And so I want to simplify a potential. And one way to do that is to say that if there is a conformal symmetry behind this, let's say these particles interact, this quark and anti-quark described by Wilson line in a conformal field theory, then there is no scale in the problem. So all these terms are prohibited just by dimensional analysis. And you know the potential exactly. So this is a conformal symmetry. then you know the potential exactly. It's just a Coulomb potential. So that's what we will be doing. We will be doing a version of the problem which you all solved, of course, in the quantum mechanics, but now this will be a Coulomb potential in a relativistic theory, if you wish. So it's some could be conformal gauge theory. Now, if you want, if you have two particles, they could be, say, for now, it's just test probes, so described by Wilson loop, which interact by Coulomb potential. Well, you have some flux. So there are some lines of electric field. To draw it like this. And the flux is not confined. So there is no confinement. It's just going everywhere. But we expect, and we know from holography, that this system, even though the flux is not confined, we expect still to get some kind of dual description in terms of a string. So there is some emergent, perhaps, a string description, which is a statement of holography. And this string theory propagates in the extra dimension, which is an ADS. Now, as I said, I want to make life simple. So we want to have, say, a 4-point amplitude to be meromorphic. And in particular, we want to suppress all emission of the particles. Well, and if you think of a gauge theory, how do you do that? The way you do that is you just take a large n limit. Large n limit. And again, as we know, what happens is this, in this case, then it corresponds to the fact is that, say, in the dual theory, let's say you want to emit some kind of closed string, for example. You want to emit it. These processes are 1 over n suppressed. So emission of color singlets is suppressed. You can ask now the following question, which is that, let's say you have this conformal gauge theory at large n limit, and you consider this Wilson loop in the same, just in the time direction of this meson color singlet state. How does it look? And the picture is the following: that you have this, and yeah, this is discussed in a paper by Klebanov, Maldacen, and Thorne from 2006, I think. What you get is that, well, you get this color. So let's look at weak coupling. You get this ground state, which is this, in this case, it's just minus, say, to leading order, some lambda 't coupling divided by L. And then you have nothing, and you have a continuous states. So there is a gap. And intuitively, what happens is that if you try to develop some excitation on this flux tube, or it's a string, the string is too fluffy. It does not support any excitations. So another way to also think about this gap, because clearly if you have a conformal symmetry, this theory is actually, of course, gapless. So what is this? Some kind of stiffness. You see there is some kind of some gapness or some stiffness. It's exactly this large N effect that if you try to emit, if you say take this quark and shake it a little bit, like say you do it in QED, well, it will want to emit, say, photons. But here, the magic of the, say, large N limit is that the emissions of the scalar singlets is suppressed. So you have this gap in the large N limit. And so say this ground state is the string. And then you can think of that if you try to shake it, the string is pulled, say, towards ADS horizon, and it just does not support any excitations. Now, I want to do scattering amplitudes for you in this model. So the next thing we need to do is we need to make these quarks. I was talking about this Wilson line. Sorry, this picture, by the way, is, let me emphasize, this is a weak coupling. Weak coupling, so lambda is small. You can ask what happens as coupling gets bigger. Well, as you can imagine, the bigger coupling, so this is the attraction between quarks, it will support more eigenstates, and indeed at strong coupling, you start having many bound states. And the physical picture for this is that what does it mean that in the gauge theory the coupling gets strong? It means that this the dual string becomes more stiff. So the tension of the string grows, and so it admits a non-trivial spectrum of excitations. So these are the standard words. This is the standard picture of ADS CFT, but maybe perhaps from this open string point of view, where you see that the stiffness of the gauge theory color flux is mapped to this, well, to the tension of the string. Now, I want to do some scattering. I want to do a 2-to-2 scattering amplitude. So I need to make these quarks dynamical. So we want to have these dynamical quarks. With some finite mass. So how do you do that? Well, there is an easy way to do that. Let's say you start with n equal 4 super Young-Mills, which is a conformal theory. So you have a stack of D3 branes. And so you have here, say, COM n equal 4. And this is a CFT, so there are no scattering amplitudes here. But what you can do is that you can go on what is known as a Coulomb range, where you take one of these branes, say, you can take one of them or several, and you move it apart. In the gauge theory, it corresponds to the fact that you turn on the VEV of some scalar, you make it non-zero, and so you break conformal symmetry spontaneously, and now you can consider this scattering of strings on this brane. So you come. And in fact, what they do is that, because you see there are many branes here, and so to leading order at large N, what they actually do is that they form a pair of massive strings, which looks like this. When they meet, we can call the strings W bosons. So they are massive. And now from the point of view of this, from the point of view of the original SUN gauge theory, this string looks like a massive quark because it has an infinite mass, which is controlled by the wave, but then it carries some charge. And therefore, if we consider, say, if we consider scattering on the Coulomb branch of n equal 4 super young meals in the planar limit, it precisely realizes, it's just a precise microscopic realization of the simple picture where we have a quark and anti-quark. The potential is just a Coulomb potential between them. This is precisely how these two quark and anti-quark interact. But now it is embedded into, from the point of view of, say, scattering on this brane, we study again scattering amplitude S and T. So this would be the target. That's what we want to understand. And this is a function here of course, a Tooth coupling, which we can define as well, the usual lambda 16 pi square, where lambda is, as you know, perhaps g squared young meals, number of colors, 16 pi square. And the planar limit is when NC goes to infinity, is g fixed. Therefore, we have a function. We have a function of ST and the coupling. And you can vary the coupling from being small to being large. Let me, and my goal would be to understand, to try to understand this function. Can we solve this problem? We know that this function exists because the theory exists. But what does it mean, or what's a physics? Now, let's start with, and here I want to demonstrate to you basically the interplay of various things that people thought about. Well, let's understand this function in the various limits. So first, take g to be very small. This is precisely the limit that we discussed at the first lecture. So the leading process is given by the one loop diagram of this type. So these are the, say, here, these modes of the string, we can take massless to end on the same brane. Or we can take here several of this brane, 1, 2, 3, 4, doesn't matter. So these are massless particles. Then when they meet, they create these bosons. And from the point of gauge theory, it simply means that as you as you turn on some waves, you generate some masses, and you exchange this massive particle here. And this is a leading result at weak coupling. And as we discuss on various occasions, well, this amplitude, how does it look? Well, it satisfies all the properties. It has a cut, 4n square. It satisfies maximal analyticity. It satisfies Mandelstam representation, etc. From the point of view of ADS geometry, what is this cut? Physically and this cut corresponds to the fact that you could have these strings go from the boundary to the ADS horizon and then move apart. This is a physical picture of the cut. Now, this is just the one loop result. And this correction to this, you can compute. People have studied this at length. It knows up to the explicit result is known up to 3 loops. There is a proposal for the integrand. But let's continue asking some qualitative questions and ask how does the amplitude look when the coupling is strong? Well, in this case, what happens, let me draw the ADS geometry. You have the horizon, say z equal infinity. You have your probe brane, we can take it z equals 1. And you have the boundary. And we consider scattering of strings on this probe brane. And as I told you, and as we expect, what happens is that when coupling becomes strong, the scattering of these strings becomes very stiff. And in fact, the scattering becomes local here, and you don't see any of this ADS geometry. So it just becomes a scattering of strings on in flat space. And indeed, what happens is that at strong coupling, this amplitude that we are studying, you can show and argue that it reproduces simply these formulas that we already saw, namely the Veneziano amplitude. Therefore, curiously enough, and perhaps it's at first it's a bit striking, but you see that we're having a function. We are looking at the function which interpolates between Feynman diagrams at weak coupling and the Veneziano amplitude at strong coupling. In particular, you see that the analytic structure here looks very different because you just have a bunch of poles and you don't see any cut. The cut is gone here in this formula. But of course, it suggests the following picture at finite coupling, that if you look at the singularities of the amplitude, you have a 2-particle cut, and you have a bunch of bound states. And in fact, we will see that there are infinitely many bound states. So these are poles or bound states. And these bound states are exactly related to excitation of this flux tube or to this state, as I will explain. But basically, we see that what happens is that at weak coupling, this amplitude is dominated by the cut. So we just see the cut, we don't see any bound states, they're suppressed. And at strong coupling, it is dominated by the bound states. We do not see any cut. And at finite coupling, it has both, so it looks quite complicated, but that's a physics. And on this picture, this cut is related to the strings going to the horizon. So the mass of the string is equal to m in this gauge theory language. That's where we put the brain. Okay. Now, let me comment on something because I think it's a bit nice. You might be confused by the two things which I told you. First, I said that when G goes to infinity, the string becomes more stiff. So T becomes big, its tension becomes big. And you know that it means that if we look, say, in the Veneziano amplitude, that this is effectively this tension. So yeah, if we send the string scale, if we make the string scale to 0, all the string modes go to the UV. And this exactly this corresponds to the string becoming stiff. The string scale, the string length goes to 0, and all the resonance should become heavy. This is what usually happens, when alpha prime string theory goes to 0. This is precisely this limit, the strong coupling limit. On the other hand, you see what happens here in this formula. In fact, all these poles, they go to low energy. So where does this gamma function has a pole? Well, it's where this thing is equal to some integer. And when G becomes bigger, this Sn is proportional to 1 over G. So we see that this stringy states become lighter. So it seems like a contradiction. How come that on one hand, I told you the strings get stiffer, so they should become heavier, but then in the formula here, they become lighter. And I think this is a very clear, neat demonstration of the holographic principle, because you should remember that so here there are two effects. One effect is that when you perform experiment here locally, then the stringy modes become heavier. But there is a second effect, which is that when you translate the process in the bulk to the language of the field theory, there is potentially a redshift, because let me remind you that in ADS, the geometry has this redshift factor 1 over z squared in front. And what happens here is that there are two effects. And if you translate S n equal 4 to which is a Mandelstam S, to the energy on the D3 brane, there is a 1 over z D3 factor. And what happens is that if you try to make the coupling larger while keeping the mass fixed, these are the units of the gauge theory, of the position of the two-particle cut fixed. It corresponds to the fact that because the string becomes, the tension of the string growth, to keep the mass fixed, you need to move the brane closer and closer to the horizon. Because you see, if the tension grows, the unit length of the string costs you more energy. And if the whole string is always m, you have to move the brane towards the horizon. And there are two effects. So first, and this is precisely this effect, and it turns out that indeed the stringy modes on the D3 brane locally, they become heavier. And this means that they go to their masses are growing, and so they in fact scale like g. But this redshift factor is also there, and it's because squared scales like g square, and the overall effect that from the point of view of the gauge theory, these states become light. This is the basic physical mechanism for how come in the gauge theory, when you go to strong coupling, you see the Veneziano amplitude appearing at low energy. It appears at low energy. This is a little bit different from the holography for CFTs as usually discussed. Now, okay, it seems like an interesting model. Let me ask the next question. What do we know about these bound states? And one thing that we know, in fact, you can show that there is an accumulation point in the spectrum. Accumulation point. And it's related to the fact that if you consider, for example, the energy of a rotating string, so you consider say string rotating on a D3 brane, and you consider energy as a function of G, of the J, of the spin, you find that in fact it goes like 2m minus something like a J square. And again, this is something we can connect to the Coulomb potential, because this is a spectrum of a familiar spectrum of a hydrogen. And so, in fact, the bound states, they develop here an ionization threshold. And this was nicely also explained in a paper by Simon and Johannes. Now, in the recent Bootstrap studies, so there is accumulation points have been coming up, but this is one example where actually this accumulation point in the spectrum, and by accumulation point, I mean that you have the two-particle cut and you have infinitely many poles as you approach the two-particle threshold. But here, again, we see that accumulation point acquires some meaning. Now, here, as I hope to convince you, this model is a pretty simple model. You see, we turned off all these terms here. We used conformal symmetry. We took the Largen limit. So, and still already it's a function which we do not have hope to write analytically in terms of some known special function, because you see that it has the cut, it has this infinitely many poles. And how would we go ahead and try to find this function at finite coupling? And here I just want to say a few words that how you can use this matrix bootstrap technique with, well, basically any other method you know in physics. You just try to combine it. For example, this amplitude's known to exhibit this remarkable property, which is called dual conformal invariance. Dual conformal invariance is something which, if you wish, it's related to the fact that when you think about this theory in the bulk, and you consider scattering of the strings, there is isometry of ADS, which is realized in field theory. And basically, you combine to get the extra dimension. You take the momentum of a four momentum of a particle, and you combine it with its roughly mass scale, which is related to exactly position of this brain in ADS. And then you realize that already at one loop, you see the manifestation of this symmetry. So this dual conformal invariance leads to things like this, as you know. And I don't have time to explain that, but again, keep in mind your hydrogen problem from quantum mechanics. And you know, in the case of hydrogen, the spectrum naively starts with SO3 multiplets. But in fact, because of the Runge length vector, the actual multiplets are SO4. So there is an extra degeneracy, there is this quantum number, principal quantum number, and there is extra degeneracy when you change the spin. And this is explained by this extra symmetry. Here, this is the same thing that happens, but now in the relativistic model. You find that, in fact, all the states, they organize naively in SO3 partial waves, but due to dual conformal invariance, they enhanced into SO4 partial waves. Something interesting. And of course, this is a simplification, because the more symmetry we have, the more chance we have to solve the model. Next, well, you can use supersymmetry. Let me not explain it. But another thing which remarkable thing that happens, again, from dual conformal invariance, is there is a connection to integrability. And the precise statement is the following. For example, let me formulate it for what is known as a leading Regge trajectory. Say if you take S to infinity, the amplitude behaves as S to the J of t. And it turns out that this function, this Regge trajectory, it's related to cusp anomalous dimension. So there is in this theory some kind of Regge cusp correspondence. The way you see it is that you use dual conformal invariance, and you take a limit where one of the conformal cross ratio goes to 0, and you see that you can realize the same cross ratio in two physically different ways. One, you can think of this as a high energy limit, and another limit that is IR limit. And in the Regge limit, you get Regge trajectories, and the IR limit, you have IR divergences, which are controlled by cusp anomalous dimension. And this cusp anomalous dimension can be computed, for example, using the quantum spectral curve. So we seem to be gaining more and more insight into this amplitude. But still, if I ask you, what happens at, say, G equals 1? No, well, we can take all this magic and say this enhanced symmetry. We can put in this Regge trajectory, and let me just draw it for you. I like this plot because, again, it also demonstrates what's the physics of this model. Is that let me first remind you that in the usual string theory, Reggie trajectories are straight. So this is a famous result. If you take Veneziano, the poles are all aligned on a straight line. Now, and if you take a QCD, it seems like they bend and they go straight. And here they behave logarithmically. So this is say G t is a function of t. And here they behave linearly. So this would be a QCD. Now, this model is a little bit in between. It's not, of course, a QCD. It would be too good to be true. But here, the Reggie trajectory looks like this. It goes like a log. Then it has a linear part, and then it goes to infinity to the accumulation point. And it turns out, through this Reggie-Cusp correspondence, this is related to different objects and integrability. For example, this region here is related to the quark-antiquark potential. We can show through this correspondence. This region here is related to what is known as a Bremse-Strahlen function, which is a cusp at low angle. This is cusp close to pi. And finally here, where it behaves like a log, it's related to the light-like cusp. All these things are computable in n-equal form. And so you see that there is a very complicated dynamics, because here you have when this line, this Reggie trajectory, remember we discussed this Chu-Fauci plot, when it crosses an integer, you have a bound state. There is a complicated spectrum of bound states. And there is also, of course, a story for subleading Reggie trajectories, but let me just continue. So now it seems like it's a very special model. Can we put everything together, and can we solve it using S-matrix Bootstrap? So let's say we put everything in.
Sorry, can I ask a question?
Of course.
So in this case, why is the Reggie trajectory? How do you see that if you have accumulation point, you would have this
Yes.
dotted line here? And also,
Very good.
what regime is like? Is it accumulation? What regime of G are we looking at for the accumulation point?
Yes, thank you for the question. So the resonances occur when this G of t crosses an integer. So these are the these points 1, 2, 3, 4, 5, etc. And you see the masses of these resonances are these points here. And what happens is, as you approach a two-particle threshold, you see that the number of this bound state goes to infinity, because this curve goes all the way to infinity here. Therefore, if you cross all the integers, you have infinitely many bound states accumulating close to the two-particle threshold. So the fact that you have accumulation point is a statement that Reggie trajectory goes to infinity. That's it. That's it.
Yeah, thank you.
And now let's just put everything together so basically I told you that this amplitude has this physics of a cut plus a bound states. You have integrability, you have enhanced symmetry. Well, let's put it all in this matrix Bootstrap. What do we get? And let's try to plot one of these low energy observables. that we've been discussing, like we discussed this almond. So let me of Wilson, the allowed values of Wilson coefficients. Now, if you do this, and okay, I spare you of technical details, you see the following picture that emerges. If you look at weak coupling, so these are some, let's say, some observables, some Wilson coefficients, you get the following shape, roughly something like this. And everything which is inside is allowed. Now, this shape has a cusp. And okay, you can try to find what the amplitude here is, at this cusp. And you find G goes to 0, G very small. You find that indeed the amplitude here is the amplitude that we're interested in, semi-equal force dependence. So this is an example, at least one example where we put so many things in. We looked at some observable, and in some limit, we actually get a physical observable at the boundary, something that happens in 3D-izing in the CFT. But if you go to, say, strong coupling, when you look at the Veneziano, it's known that there have been several papers last year. It's known that Veneziano amplitude is not, or at least not obviously on the boundary. Yes.
Could you just clarify what these axes are?
Yes. So the axis. Thank you. Again, you take, say, the amplitude. You expand it at low energies. You define this Wilson coefficients, AKN, and you define some dimensionless ratios using the gap. And so effectively, you have here, say, A10, A20, yeah, divided by A00. So these are these observables, which are defined by low energy expansion of the amplitude. And at strong coupling, you also get some shape. Let me just, you get some shape, which also must be convex. I don't remember the details of the shape, but the point is that Veneziano amplitude is not at the boundary. And then, in fact, you can use you collect all the known weak and strong coupling results. You can model these observables using some kind of Padé approximations. You see that they we started as you change the coupling, the theory makes a pass in a theory space where it roughly goes from one corner at weak coupling to somewhere close to the other corner at strong coupling, but it stays inside. And then you can use this matrix Bootstrap to characterize this path. And because usually if you do some kind of Padé approximation, you cannot really control it. But here you can combine it with this matrix Bootstrap to get some insight. And so this is an example which perhaps the simplest example of scattering in 4 dimensions, which we know. It's a deformation of Veneziano amplitude. It has lots of symmetries. It has lots of structure, and even then we see that, say, the S matrix Bootstrap by itself, when combined with other things, it becomes useful. But say in this case, it's not enough to completely solve the theory. You go to the boundaries, you get something in physical. There are many more things that's happening. So perhaps I will stop there because I'm out of time. But I would just conclude this lectures with maybe reminding
Sasha,
you.
you're not out of time. This
not.
lecture is from two to 3:15 our time, so you have
Ah,
15
I have
minutes.
15 minutes. Oh my God. That's such a good news. So because I skipped a lot of things because I thought indeed I'm out of time. But maybe you know what? Why don't we just then talk for 15 minutes? If you have any questions, and you can ask me to explain more what was not clear. But let me just summarize again the basic.
Sasha, sorry.
Yeah.
Can I ask you a question?
Let's
Sorry,
go.
it's because I missed this part of what you said. Maybe you
Mhm.
have mentioned it, but for the large engaged theory, I think you said it's a conformer. It's a CFT, but when this scalar field develops some web, does that break the CFT? Is that why you are considering like other form of the
Exactly. Yes. Exactly.
But then because
So
it's the web
yeah.
of the scalar, isn't it a spontaneous breaking of the conformal symmetry?
Yes. Yeah. It's a spontaneous. Exactly. It's a spontaneously broken conformal symmetry.
But then
So
why the amplitude? Why you can't compute the amplitude using the Lagrangian or if it's just a spontaneous symmetry breaking?
So you can compute the amplitude using Lagrangian at weak coupling. So this is precisely the computation using the Lagrangian. But if you want to know the physics at finite coupling, then it's very hard. Because, for example, if you want to see this pole, any of these poles, you have to resum infinitely many Feynman diagrams. So this is a finite coupling effect. If you do perturbation theory, all the Feynman diagrams, they just look like this. So you don't see any poles. So there is a lot of, if you wish, non-perturbative, or there is some non-perturbative physics. And even though you're absolutely right, you have Feynman diagrams, you have a Lagrangian, but this just with coupling. It helps you with coupling.
I see. Sorry, just one last.
Yes.
If the symmetries is still there or respected by the Lagrangian, why the S matrix is not?
Well, the symmetry is spontaneously broken. You have massive particles. These massive particles are dynamical. And just imagine, just think about what we are doing. Let's say here we have some strings, they have some wave packets, they scatter, they create these bigger strings. These strings then can collide, they interact, they can exchange all kinds of color flux here. There's this in the colored soup. So there is a lots of non-trivial dynamics, and it is what the physical picture is, but computing it at finite coupling is hard.
I see. Thank you.
Hi, can I ask a bit more about the dual conformal invariance explanation that you were giving?
Yes,
So,
please, yes.
I'm unfamiliar with this partial wave perspective on it. The one I'm familiar with is you change momentum to this twistor space that are differences of stuff. Can you tell us a bit more? And then I can just see that there's conformal invariance in this space, but it's not obvious from the original amplitude. So are you saying that in the partial wave basis you do somehow see this even in the original picture, or how should I understand this?
That's right. The idea is the following, that perhaps the simplest, well, maybe not. Let me just try it like this. So unitarity here. So if we look at the amplitude as some mass, there is some mass, there is a pole. The states here should organize in terms of the partial waves, which are SO3 partial waves. The usual story, you have the angle. So this is the usual the usual unitarity, and all these CJs are non-negative. This is the usual unitarity. You can check for the Veneziano, for example. Now, from what I said, it's completely not obvious, of course. But the claim is that, in fact, yeah, I think it was first explained again in a paper by Simon, again Johannes Hahn. That was the third person. If you look at the spectrum in this model, and you think about the scattering process in say in now this ADS5, you realize that if you think about say the center mass collision, what is the little group that preserves this this configuration? You get instead of you get the following story that let me remind you that the energy again, there is a cut, 4m squared, and there are bound states. So for bound states, you get that the little group gets enhanced to SO4, which means that this sum, in fact, can be written as a sum of PJ SO4. And curiously, you get here some deformed argument. Sorry, let me write it as n squared. N squared minus 2. Square. So, and if you go here for the cut, you can show that you get instead the continuum of SO13 harmonics. So again, with the same deformed angle, and the way to literally think then, well, if you take any of this SO4 Legendre polynomial, you can decompose it as a positive sum of SO3 Legendres. So it literally packages some degeneracy, which you don't see in this formula, but you take one of these Legendres and you get a finite sum of these guys. And the same here, you take this harmonics, which again, this group appears if you think of scattering in this dual ADS space. And this is very important because precisely this fact that you have higher enhanced spherical unitarity is responsible to the fact that you find n equal 4 at the cusp. If you look at the picture in the usual SO3 spherical harmonics, it looks like this. It just goes to the origin. There is no cusp. So this cusp is due to dual conformal invariance. And the amplitude that lives at this cusp is precisely this one loop box. This one. So this is an extremal amplitude from the point of view of dual conformal invariance. Now the way, perhaps one way you can think about this SO4 is that if you imagine the scattering process in ADS, and then you think these two strings collide and they create some state with some energy, and you just look at the transformation of the part of dual conformal invariance which preserves the state, like we usually do. Is if I collide in the center of mass, I have a state with some energy E and 0 momentum. And now the transformation which preserves this is SO3. You can rotate it; it doesn't change this momentum. It's a fixed point. If you do the same exercise in ADS5, this is what you get. And so, and this was, for example, used in this paper.
Okay. Maybe if I can ask a follow-up question, it would just be, is there a simple explanation for why this would require dual conformal invariance? Because I guess from my understanding, the fact that you can do this dual transformation or so, why do you need dual conformal invariance and not just conformal invariance? What would change in this argument if you just had conformal invariance? for any use for?
Well, the conformal invariance is here is broken, and the dual conformal invariance it is dual because it really acts in momentum space. You know, you do the usual you do the usual T duality, and you introduce this T dual coordinates, and then the conformal invariants act effectively on them. So I actually I do not I'm not sure how to see the remnants of this spontaneously broken conformal symmetry here. Well, beyond, you know, if you have spontaneously broken conformal symmetry, you have soft theorems for dilaton, things like that. So, and these are realized here, but beyond that, I'm not sure what's, it's an interesting question, yeah, because you say maybe you're saying maybe if there is a conformal invariance, dual conformal invariance, there is some Yangian. Yeah, I don't know. It's.
Thank you.
Hey, thanks for the nice talks. I was actually glad you brought up this one loop Coulomb branch amplitude, because I've been a bit confused about this in the past, because this kind of diagram comes up in multiple places. On the one hand, it's the thing you can calculate on the Coulomb branch. But on the other hand, sometimes people talk about these Higgs regulators because putting this mass on the loop kind of takes care of your soft and collinear divergences, right? And so I was wondering, are they literally related by some kind of Higgs mechanism argument where you have a massive scalar and you keep the gluonic modes kind of standard and the W and you just repackage them? Or are these two things which are just kind of confusingly similar at a glance?
Well, let me try to say some, maybe answer, but yeah, the way I think about it is literally we start with n equal 4, we turn on the VEF, we have we derive the Feynman rules, and then what you see is that due to the large n effect, what happens is that you develop this W boson massive frame, and then you start filling it with gluons. So you have massless gluons, which are planar diagrams made out of massless gluons with this frame. And here, this is not, well, I'm not really thinking this of as a regulator, because you know, it's, to me, there is a theory behind, there is a space of states, they live in the multiplets, this whole thing satisfies unitarity. Of course, you can just use it as a regulator, well, for some separate graphs, but I'm not sure. Here, for me, it's crucial that it's not just a regulator of some Feynman diagrams, but there is a theory behind which satisfy all the nice axioms which I can use. But I'm not sure if it answers your questions.
Maybe if I can just follow up on that, just to kind
Yeah.
of try to clarify. So if I wanted to use it as a regulator, I'd be perfectly free to talk about pure gluonic, like n equals 0, just with some massive scalars on the rim, but then that would not be related to the Coulomb branch whatsoever.
Yeah.
Okay, great. Thanks.
Yeah. So then I would just perhaps so at the level of Feynman graphs, perhaps many things, maybe or some things can be said, but at the level of, say, finite coupling, I wouldn't know what to say. So, for example, you see here for me it was let's say you're a Feynman diagram person. You start with these loops. There are infinitely many loops, and I ask you what happens at strong coupling. If it's some regulators, I wouldn't know what to say. But here it was just you say, well, let me look at the holographic picture, and here I know what happens is that the strings just become stiff. They become very small, and so then it becomes just Veneziano in flat space. So, and I immediately can write this answer without having a theory in mind. It sounds like an impossible task, because even if you're a Feynman diagram person, seeing these poles is incredibly hard, because to all loop orders you just have a cut. This comes really from the summation of infinitely many Feynman diagrams. Yeah. Maybe since it's now
I was going to say, Sasha, we're just at time. I see one more.
Okay.
See one more question in the room, so
Sure.
it may be easier to take the question in this same
Yeah.
form.
can go a few minutes more.
Oh, of course, yeah. Was there.
Can I ask, so you told us this very nice story about 2-to-2 scattering, and particle production, of course, is part of the story. But in collider experiments, inclusive amplitudes are very important.
Yeah.
Can any of these techniques put bounds on these types of objects?
So this is something I'm really interested. So let me tell you some fact which I find curious, which is that usually, let's say you want to do 4D gravity or collider physics or 4D QED, then amplitudes are IR divergent, or if you want to make them IR finite, you have to understand some subtle dressing, and computational becomes very hard. So what's the simplest observable to compute, which is IR finite? Well, you can compute the following observable. Take an inclusive cross-section of, say, 2 gravitons going into graviton plus whatever. So you have your beams, you detect 1 graviton, and for the rest you sum over. This is a IR finite object, which depends on 2 variables. It depends on, well, S, and it depends on angle. This is the angle. This is precisely the inclusive cross-section, and you can compute it in pure gravity or in supergravity. It is IR finite. And it exhibits some of the properties which we have here. For example, the analytic properties are the ones of the amplitudes. You have 2 cuts. Well, it's a cross-section, so it's positive. So it seems nice, but it seems to me that some of this, and perhaps there is a way perhaps to think about it, but it seems like, let's say you have something like C d phi to the 4th, and you know that unitarity can constrain the sign of C to be, say, whatever, positive or negative in some convention. But if you compute this cross-section, it's a C square. So you do not see the sign. Of course, you can see the sign if you start doing some inclusive experiments, which are more complicated, where you collide 2 particles, and then you say, I don't care what happens here, but here nothing should come out. So I look at the cross-section of this graviton coming earlier than the light cone, then it should be 0 by causality. So there should be a constraint. And presumably this works. So if we do 4D gravity and we set up the experiment where 2 gravitons come, and I detect 1 graviton, and here goes X, and I impose that this cross-section is 0, this should put some bounds on, on this theory, but it's not as clean. Here, the magic of this analyticity is that it's just S and T. It's just very simple. But if I start doing wave packets and I do a 3rd wave packet, it seems like some of these things are lost. And so I'm very interested in this question, but I don't know if, in fact, there is also, let me just mention that there are Fox-Wolfram bounds. It's a most famous paper by Stephen Wolfram. There are these Fox-Wolfram bounds on the collider observables, which are bootstrap in nature. But again, it seems like not powerful enough. So I think it's a very interesting question, and perhaps there is the right way to think about it, where it can be done. And so, yeah, I would like to understand it. Thanks for the question.
Thank you.
All right, so I think we'll end the questions here since we're a little over. So I just want to remind everyone, as we're saying thank you to Sasha for his lectures, that he was also one of the organizers of the school. He put the scientific program together. And so when we're thanking Sasha, let's thank him for all of his contributions to TASI 2025. Thanks.
Thanks, Oliver. And